Okay, so let's start with this problem. So you had in 1.1, I believe, or maybe 1.2, you had exercise number 90, I think, as your homework. And I will just show you something similar. That would be the next problem, 91. This is asking to show the graph is the lower half of the circle and then determine the domain and the range. So in some of the cases, it's easier to find the domain and range by just graphing the function. This way, it might be very complicated and difficult to see what's going on, right? But usually you can bring your function to a form where it's easy to see those transformations, right? So in this case, we essentially have y equals to 2 minus square root of negative x squared plus 6x plus 16, right? And we want, so we are given already some kind of a hint that that should be a lower part of the circle, right? So we want to see where the circle or semicircle is in this case. Remember that the equation of the circle is r squared equals to x squared plus y squared, right? Where r is some number or radius, right? So if we solve for y squared in this case, we'll have r squared minus x squared, and then we have y equals to plus minus square root of r squared minus x squared, right? And since we are given the lower half circle, then we will just be working with the negative part of it, negative branch of our circle. Okay. Give me a second. Okay. So, yeah, I'm right now I'm like between you guys and the emails students sending me with the passcode for for this session. So, I might just, keep silence for a second or so, and then I'll come back. Okay, so we want to see, or we want to bring our equation or function to resemble this form, right? So first of all, what we can do here is we see that we have this kind of a parabola hidden here or something with a square, right? So what if we just try to complete the square with this too, and maybe we can see that there is some shift with x going on, and this 16 is a part of our radius, right? So let me rewrite that as 2 minus, so let me move this one to the front first. So I have 16 minus x squared plus 6x, right? So this way it's kind of easier to see maybe that this should be a part of my r, and this should be some x plus or minus some shift. I forgot, it's probably h or k, one of those squared. So I want to bring it to this form, right? Okay, so for that one, I will just try to complete the square. So I have 2 minus 16 minus, so I have x squared minus 6x plus something. What is this something should be? So remember that by the formula for completing the square, we have 6 over 2 squared, right? So that's going to be 3 squared, which is 9, right? So now we will have 2 minus square root of 16. Oh, also I forgot to add there. So if we add plus 9 here, we also need to subtract 9, right? To keep the balance. But since this plus 9, if we multiply it by this negative in front of it, that's already minus 9, right? So we need to again add another 9 to keep the balance, right? Because this negative will affect this positive 9 in the parentheses. So we'll need to minus 9 plus 9, right? Okay, so what I need to do right now is combine these 16 and 9, right? So I have 16 plus 9 minus, I have this x squared minus 6x plus 9 here. Now let's simplify everything. So I have 2 minus 16 plus 9, that's 25, minus, what do we have in the parentheses? So I have x minus 3 squared, right? Now this is better, right? Because now we can see that this guy, this part right here is actually resembles our semicircle. With the minus, that would be also the lower part, right? So what we need to do from here, I will just draw a number line or XY plane, right? And then let's look at just a regular r squared minus x squared, right? So in our case, what is r? What is our, what's it called? The radius. It's gonna be 25, which is 5 squared, right? So we have 5 squared minus x squared. So I'll start with a semicircle of a radius 5, okay? So I'll probably need to do the whole circle because it's easier to do it this way on. So 5 here and negative 5 here. So let me see how we can. All right, beautiful. So, okay, so this is my full circle. Let me erase the upper half. Okay. So far so good, right? So this is my square root of negative square root of 5 squared minus x squared, right? Now, we have some shifts in here, right? So first shift, we have 3 units to the right, this side, and we also have, 2 units up, right? So whenever you have it outside, that's up or down. If you have something together with x, that's gonna be left or right. So what I need to do is, so I will just copy the one that I have, and I will start moving this one. So first I move 3 units to the right. So 1, 2, 3 units to the right and 2 units up, right? So 1, 2, 2 units up. So this is my new updated semicircle, which has the coordinates here. It's -2, right? Because we're moving 3 units from -5. We move 3 units to the right, and this 5 moves, that kind of should be a little bit like this. Okay. And 5 units to the right, that's gonna be 8 here. So this points are -2 and 8 on the axis. Now here we had 0, right? We moved 2 units up, so that's gonna be 2. We had -5 here. Again, we moved 2 units up, so that's gonna be -3, right? So we have everything. We can now erase our original circle, and this is the circle that we have with all the transformations, right? So this is the same circle as we were, as we were given at the very beginning, right? So now from here, I think it's easier to see what would be the domain and range, right? So we have domain is gonna be from -2 to 8, right? And the range will be in this case from -3 to +2, right? So this is your range and domain. If so, you can see sometimes it's easier to work this way. Do you have any questions? Okay, so let's move on then to next one. So let me show you a couple of more graphing transformation problems. that we didn't have a chance to cover in class. So I have y equals to x minus 3 squared. Okay, give me a second. So, okay. So, again, we start with the regular parabola, right? So x squared. And as you can see, we can just move it. This one is not that bad. It's pretty easy, right? So it's x and y. So we start with the regular parabola, which is 1, 1, negative 1. So here, 2 and 4, 3, 4, 4 right here. Okay, so we have the points here and here. So this is my, oops. Okay. Um, Let me see. Okay. Something like this. Okay, so this is the just the simple x squared parabola, right? But now we have some transformations here, right? So -3, what does it mean? That means that we're moving 3 units to the right. If it was +3, we will move 3 units to the left, right? So if you have also, let's say, +4 here, for example, then you will move your parabola 4 units up. If it was -4, you would move every single point 4 units down, right? So these are kind of the things that you need to keep in mind. So since I'm on the iPad, I guess for me it would be easier just to duplicate it and maybe choose another color. So let's say like this, and I will be moving this one on a piece of paper. That would be, not so easy to do, but you get the idea. So all the points are moving in this case, 1, 2, 3 units to the right, right? So we're looking at 0, 0, right? It will move 1, 2, 3 units to the right. We will look at -1, 1. It will move 1, 2, 3 units. And this one will move also 3 units. So that's going to be here. And every single one of those points will be moving 3 units to the right. So this is where we end up with this specific problem. Now, since I added +4, why not just use that? So this point right now, we will move it 4 units up. So that will end up right here. This point will end up here. This point will end up here. And a which one? This one would be 2, 4, well, approximately here because I have like not the full thing. So 2 here, like this. So I will have my new parabola, which I will probably use another color. Right? So this is my now transformed parabola x minus 3 squared plus 4. Okay? So if you have a problem on exam, something similar to this, if you want, you can keep all of your transformations on the graph, right? So let's say you start with this one, then you move it to the right, move it up, or you can just write the final answer and let's say erase this two. It doesn't really matter that much as long as you have the parabola in the correct spot. If you think that you might make a mistake in, transformation of those graphs, I would suggest you to keep all your previous steps without erasing them. Just maybe mark them. Let's say this one is x minus 3 squared. This one is x squared so that I can see exactly your like what you were doing and how you were moving your your function to spot the mistake and if it's uh, crucial or it's okay, just not so much. Okay, so this is for the parabola. Now if we have something a bit more involved, like y equals to x squared minus 4x plus 5. All right, so again, when we see x squared, we first thing we know that it's gonna be probably a parabola, right? And I don't want you to do it this to graph it the way that, let's say, with the discriminant and finding the um, what is y-intercepts, I want you to complete the square to have it in a form, let's say a x plus, is it k or h? I think it's maybe k squared plus h, something like this. So when it's in this form, it's easier to graph it because you have your stretch or compression, you have your um, shift to the right or left, and you have your shift up or down, okay? So in this case, to get to this form, we will need to complete the square, right? Because it's not perfect square. We cannot write it in a way that x plus or minus something, right, squared. So we need to bring it to that form. Again, so how we can write it is x squared minus 4x plus something, then minus that something, right? To keep the balance, we need to add and subtract, and then plus 5. Okay, so what that something should be. So remember by the formula, it's 4 over 2 squared, right? So whatever your value is, so ax squared plus bx plus c, that would be b over 2 squared. That was the formula for completing the square, right? So you will put that in between this, like right here, that would go here, and minus the same thing, b over 2 squared, right? Okay, so what we have here, that's going to be 2 squared, that's 4. So instead of this question marks, we will put 4 here, right? And we have x squared minus 4x plus 4. That would be in our perfect square. And then we have the leftover negative 4 plus 5, which is just plus 1, right? Another way to do it is just decompose your 5 into 4 plus 1, also works. And you can keep that 4 to complete the square, and plus 1 is just kind of a neighbor that kind of stays there separately from them. Okay, so this one we can combine into x minus 2 squared plus 1, right? And now again, we can easily graph this parabola. This will have 2 units shift to the right and 1 unit shift up, right? So if I just briefly kind of quickly draw it, and then I move it 2 units to the right and 1 up, I will have something like this going on, right? So my vertex 0, 0 will shift to 2 comma 1, right? And you can also see it from here. All right, so this is the way that we would draw this parabola. Now I want to show you another graph, which would be, so I highly recommend you to memorize this, the graph, sorry, the how this graph, this function looks like, right? So this is very, very fundamental, I would say, function. So we start with this one, and then I'll apply some transformation on that. So whenever, first of all, we have an asymptote at like make it bigger. Okay, we have an asymptote at y equals to 0, and we also have another asymptote at x equals to 0, right? So we have something around those asymptotes. Now, whenever x is a positive number, my fraction will be also a positive number, right? So I will have a graph right here, and whenever my x is a negative number, my whole fraction is negative, right? Because we have 1 over that, let's say -2 or something like this. So I will have the second branch would be in the third quadrant. So the graph looks like this. Oops. Okay. So it will always kind of be moving towards this asymptotes, but never touching them or crossing them in the same way here. Now, important point right here and here would be if x is -1, your y would be 1 over -1, which is -1. And when x is +1, your y would be 1 over +1. That's going to be 1. So your important point here is 1 comma 1. And here -1 comma -1. So that's for this one. If you have something like 2 or 3 or 4 here, this y coordinate will change, right? So keep that in mind. But the most basic one is gonna be this one, okay? So I would highly recommend you to kind of memorize how this function looks like. It will be very helpful just to have it in the back of your mind, right? Somewhere in the memory that, okay, so when you're working with this type of functions, you have kind of the idea how it looks like. All right, so now let me apply some transformations. So what if this 1 over x is now negative, right? So what does it mean? That means that this branch will be reflected here and this branch would be reflected down here. So we're kind of flipping them, right? So let me grab another color. I guess this one would be good. So now this uh, this branch will now be flipped here, and the one that is in the first quadrant will be flipped in the fourth quadrant. So let me erase this one so that it doesn't confuse you. So this is what we have when we have this negative, right? So we will have this transformation, and you can always check it with just some I don't know, some test point. Let's say x is equal to -1, then your fraction becomes -1 over -1, which is negative times negative gives you positive. So your y will be positive. So your point is -1 comma 1, which is right here, right? And the same goes for this branch as well. Now, if I want to apply another transformation, let's say 1 minus 1 over x, this is the same thing as saying -1 over x plus 1, right? So this guy will just give you a shift up, right? So you will just grab your function and just move it one unit up. And because of that, your what's it called? The asymptotes will also shift as well, right? They will also change. So now your asymptote is y equals to 1. This one stays, right? Because since you were moving 1 unit up, your asymptote will also move 1 unit up, okay? If you have any questions along the way, ask, okay? So that's this one, and then another one that I wanted to show you that is, I think, fun. So y equals to absolute value of square root of x minus 1. Okay, it's not that bad as it looks actually, because again, we start from the inside, right? So look for something that is easy to start with, right? So again, you need to remember how your x cubed looks like, the graph, how the linear function looks like, which is just first power of x. You need to know how your parabola looks like. You need to know how your square root of x looks like, and it is very beneficial when you know how 1 over x looks like. I think that, oh, another one is absolute value of x, so that's going to be this v-shape thingy, right? So this one is like this. 1 over x, as we said, that's going to be kind of this type of function. X is just a line, right? So depending on what you have, your M and B, parabola is just parabola. This one is like the, oh, well, kind of like that, right? Looks like tangent somewhat, right? So that's gonna be this one. Okay. Cotangent actually. Right. So going back to this one, so we start with the square root of x function, right? So let me start drawing that approximately. So I have 1 here, let's say 2, 4 here, and 2 here. So I will just make it a bit bigger than For some reason, it's very difficult to draw it right now. Okay, so this is your regular square root of x, right? Now, what I want to do, I want to continue working on the inside of my absolute value, right? So I will need to do something with this -1. What does it mean when we have -1? It's a shift down, right? If it was plus, it would be shift up. And then if you have something like minus something, like let's say square root of x minus 3 minus 1. So you would shift this one to the right 3 units and down 1 unit, right? So again, that's just like a reminder. So let me grab this beautiful graph, duplicate it, and shift it 1 unit down. So that's going to be right here. And let me change the color, I guess, so that we can clearly see. So that's going to be my square root of x minus 1. Okay, now the last step is applying this absolute value. What does it mean? So whenever your expression inside is negative, right? This absolute value bars will make it positive, right? So everything is beautiful right here because our function is positive or greater than 0 on this portion. But when we are in this portion, take some x's that are from this portion, absolute value will make them, this y, all the negative values will make it positive. So what we will have, this piece will be positive. So it will be like this. It will be kind of reflected. So you don't have it here anymore. You have this piece reflected like this, and you continue on with this portion as it is because it was still positive at the beginning. So these absolute values do not play that much role for this portion. But for this portion, it will undo the negative and make it positive, right? So when you had, let's say, the point right here, which is a 0, right? So your x is 0 in this case. So when you have the absolute value square root of 0 minus 1, that would be just absolute value of -1, which is +1. So you will not have a point right here. You will have it here. So this is your 0, comma 1. Okay. And that goes for all of the values that were negative here. Okay. So your final answer or final graph is this one in blue. Yeah, in blue. Okay. So that's what I wanted to show you about the graphs or graphing the function. Now let's go to probably 1.4, I think, because we didn't get that much practice, I guess. So what you need to remember for future, maybe not exactly for this exam, but for all the next exams, right, is Pythagorean identity. That's a huge one, right? So you need to remember that for the rest of your life, I guess, if you're doing STEM career. So this one is the one that you need to remember. Now, for the other two, I don't think that there is a need to memorize them because you can easily derive them. So let's say for the second one, what you can do is just divide everything by sine squared alpha. And what do you get? So these will cancel. So you have 1 plus now cosine squared over sine squared, that's cotangent squared alpha. And now 1 over sine squared alpha is cosecant squared alpha, right? So boom, you have a second identity done. Now, what if we take again this sine squared plus cosine squared equals to 1, and now this time we want to divide. We want to divide by cosine instead, right? So cosine squared alpha, cosine squared alpha, cosine squared alpha here. So now what do we have? Sine squared over cosine squared, that tangent squared alpha, plus cosine over cosine, that's going to be 1. And that is equal to 1 over cosine squared, that's going to be secant squared alpha. And boom, you have your last Pythagorean identity. So you don't need to kind of memorize them if you still haven't, but then or forgot, then it's important just to remember this sine plus cosine one, and the rest you can derive. Now, we have also a double angle identity, which is very important to know, especially for calculus 2 and I would say differential equations, probably. For calculus 1, maybe not that much, but it doesn't mean that we will not use it, right? So sine 2 theta, right? So the formula is 2 sine theta cosine theta. How was it derived? Like if we don't, let's say we don't remember that. For this, well, I think it's easier to remember this one than remember I forgot what it's called. Sum sine of a plus b equals to sine a cosine b plus sine b cosine a. So I forgot the name of this formula, but this is essentially what we're using to derive this double angle identity. And it's actually it's a good idea to remember at least one of them. There are four, right? One with the negative, which means that if you have a negative, then this would be just a negative. When we have a cosine a plus b, then your expanded version, I guess, would be the cosine A, cosine B. So cosines go together and sines go together as well. But now for the cosine, the whatever sign you had in the argument, you will have the opposite of that. So and then let me put that. So if it was minus, that would be plus. If it was minus here, that would be minus here. So for sine, whatever sign you have inside, that would be the same sign when you expand it. For cosine, the signs are changing, right? So you had a plus, it will be minus. You had a minus, that would be plus. And again, for cosine, you have cosines together, sines together. For sine, you have sine, cosine, just changing your arguments, okay? And from here, you can easily derive this formula. So let's say when we have sine 2 theta, that's the same thing as sine theta plus theta, correct? And then we will apply this formula right here. So we would have sine theta cosine theta plus sine theta cosine theta, which makes it a 2 sine theta cosine theta, right? So easy. Same goes for cosine 2 theta. If we apply the same rule right here, we have cosine theta plus theta, right? We have cosine theta minus sine theta, which makes it a cosine squared theta minus sine squared theta. So this is one of the formulas. Now again, applying the Pythagorean identity, you have cosine 2 theta. So we have cosine squared theta minus sine squared theta. So now I want to change this sine squared theta to 1 minus cosine squared theta, right? Using the Pythagorean identity. So I'll have cosine squared theta minus 1 plus cosine squared theta, because this minus will affect this minus as well, right? And then from here, I have 2 cosine theta, cosine squared theta minus 1. So that's another one. If I decide to make this one as 1 minus sine squared theta, so let me erase that one. Then I will have 1 minus sine squared theta minus sine squared theta, which is 1 minus 2 sine squared theta. So these are all, let me mark that, all three formulas for the cosine 2 theta, right? For sine, we use usually only this one. Okay, so this is probably one of the good ways to memorize these formulas if you haven't or forgot about them. So it's always easy to derive them. Okay, now let me go over a couple of examples that are trig related. Yeah, so let me go over this one. I have solved 2 cosine squared theta equals to 1. So I have a restriction on the domain. My theta should be between 0 and 2 pi, meaning that it is just first cycle, right? So what I need to do here, I need to solve for theta, right? I need to find what my theta is actually. So I'll start moving things away from my cosine to essentially, by the end, isolate my theta, right? So I have cosine 2 theta equals to 1 over 2, and I will square root both sides. So I have cosine theta equals to plus minus square root of 2 over 2, all right? Now, I need to recall for what theta my cosine is equal to square root of 2 over 2. So if you recall the unit circle, right? I have square root of 2 over 2 right here, right? And then this one would be, okay, so we're looking at cosine, right? So we have cosine and sine, right? So cosine have a coordinate of 1 right here, and sine has a coordinate of 0. And then on the top here, oh, actually, let me move it a little bit down. On the top here, my cosine is 0 and my sine is 1, right? So cosine and sine. Okay, so now remember that we have the square root of 3 over 2 and 1 over 2. This is what the students usually make mistakes. They're mixing where is cosine square root of 3 over 2 and 1 over 2. So if we look at the cosine only, right? So let me just kind of mark it this way. You see that we have 0 here and 1 here. Which one is greater, square root of 3 over 2 or 1 over 2? Which one is greater in magnitude? So this one is greater, right? So we'll make that like a sign. So if I have a number line, let's say, and I have 0 here, 1 here, my middle is that square root of 2 over 2, right? So I know that since square root of 3 over 2 is greater than 1 over 2, then this one should be closer to 1, right? So this is where I have my 1 square root of 3 over 2 and 1 over 2. So my cosine will be square root of 3 over 2 on the top here and 1 over 2 on, oh, sorry, the other way around. I was looking at sine. Square root of 3 over 2 here because it's closer to 1, right? And 1 over 2 here because it's closer to 0. For sine, the other way around, right? Since 1 is right here and 0 is here, then sine would be 1 over 2 at pi over 6 and square root of 3 over 2 at pi over 3, right? And both are square root of 2 over 2 on this 45 degrees or pi over 4. So remember that we have square root of 2 over 2 at pi over 4, right? So we can say that theta is equal to pi over 4, but you see that we also have a negative square root of 2 over 2. So we need to count, and also the restrictions on the domain is the full cycle, right? So we know that cosine is positive where? It's positive here in the first and the fourth quadrant, and it's negative in the second and the third quadrant. So we need to include all of those values, right? Now, a good way to memorize the values for the rest of the quadrants for those radian values is, so for the second quadrant, we have n minus 1 pi over n. This one would be n plus 1 times pi over n, and this one is a bit different, so that's 2n minus 1 pi over n. So let me kind of go over that a bit more in details, I guess. Let me redraw that. Okay. Okay. So you need to memorize this first quadrant that there's, no way around it, right? So this is my pi over 6, pi over 4, and pi over 3, right? So it's always a good idea to memorize at least this first quadrant, right? Now for the second quadrant, we have something pi over 3, something pi over 4, and something pi over 6, right? As I said, we have n minus 1 pi over n. This is just easier to memorize it, I guess, or like all these note values. So with instead of this something, right, we will have, so whatever you have in the denominator, you just subtract 1 unit from, or a point from that, and that would be your numerator. So you have 3 here, so that would be 3 minus 1. That's going to be 2 here now. So 2 pi over 3. Now for the second one, we had 4, right? So 4 minus 1 pi over 4, that's going to be 3 pi over 4, right? So that's going to be 3 here. Now for this one, we have 6 in the denominator, so it's 6 minus 1 pi over 6, that's going to be 5 pi over 6, right? So 5 pi over 6. So, and this is your notation, or the for all the radians. Now for the second or third one, you will have the same thing, right? So it's something pi over 6, then pi over 4, and pi over 3, right? We just need to figure out what these values are. And remember, by the this kind of formula, it should be denominator, whatever the value of in the denominator, plus 1. So you had 6, it's going to be 6 plus 1. So it's going to be 7 here, 7 pi over 6. Now for this one, it's going to be 4 plus 1, which is 5 pi over 6, as over 4. And for this one, it's going to be 3 plus 1, which is 4 pi over 3, right? So this one also is just 1 more than the denominator. This one is 1 less than denominator. For the last one, it would be just a little bit different, because we would have here 2n minus 1, right? Pi over that n. So when we had here pi over, let me start from here. So pi over 3, right? So 2 times 3 minus 1, that's going to be 6 minus 1, that's 5 pi over 3, right? So that's going to be here 5. Now, next one is, we have in denominator, we have 4. So what is this value here? It's going to be 2 times 4 minus 1, which is 8 minus 1, 7, right? So 7 pi over 4. And for the last one, we have, this is pi over 6. So 2 times 6 minus 1, that's going to be 12 minus 1, that's 11 pi over 6, right? So this is the way to kind of easier memorize the rest of the unit circle when you know the first quadrant. So you need only to memorize the first quadrant and maybe a couple of those formulas, I guess. to make your life easier, because eventually you'll be doing a lot of this type of exercises, right? So going back to our problem, we need to figure out where my theta is, sorry, my cosine theta is plus or minus negative square root of 2 over 2. So that's going to be this one, right? Then this one, and this one. So all these four values would be the answers for my theta, right? So I included pi over 4 already. Now the next one is 3 pi over 4, 5 pi over 4, and 7 pi over 4, right? So these are gonna be all my solutions for the first quadrant. So 3 pi over 4, 5 pi over 4, and 7 pi over 4. All right. So yeah, that would be the solution for this problem. And yeah, that's it for this one. Do you have any questions? Okay. Now let's go to the next problem. All right. So let me go over probably okay. This one probably is good. Okay. So I have yeah, let's do this one. 4 cosine squared 2 theta equals to 3. Okay. And the restrictions on the domain is from negative pi over 2 to positive pi over 2. Okay. So now what we have is cosine squared 2 theta equals to 3 over 4, right? Now we take the square root of both sides and we have cosine 2 theta equals to plus minus square root of 3 over 2, right? Okay, so now let's look at the unit circle again. And look at the restrictions on the domain. So we have from negative pi over 2 to positive pi over 2. Remember, we have 0 here, pi over 2 here, pi. Oh, actually, let me write it not in marker. So we have 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? But we are restricted from negative to positive, right? So we are looking at this branch, sorry, this portion right here, and then that's for this one. And then we also need to include the negative pi over 2. So that means that we're going clockwise direction and we are looking at this negative pi over 2 right here. So we're going this way and this way. So we are working essentially only with these two quadrants, right? And from the answer that we got, we have plus minus square root of 3 over 2. But since the domain in our case is from negative pi over 2 to pi over 2, we do not have a negative answer for my cosine because cosine is always positive in the first and the fourth quadrant, right? If it was, let's say, first and the second quadrant, right? So then we will include that negative because cosine is negative at this on this interval from 0 to pi, right? But in this case, we're not including this negative. So what we have is cosine 2 theta equals to just positive square root of 3 over 2. Okay, now if we treat our, let's say with alpha is 2 theta, then we have cosine alpha equals to square root of 3 over 2. Now, when is my cosine alpha equals to square root of 3 over 2? For what values of that alpha? So alpha is equal, again, let's go back to our unit circle. So cosine is equal to 1 here, so square root of 3 over 2 would be here, right? So we have square root of 3 over 2 right here. Then we also have it for the negative 1, we have it here as well, right? For the 11 pi over 6. So pi over 6 and 11 pi over 6, right? Okay. Right. So let me write that. So we have theta is equal to pi over 6, and so we don't include the 11 pi over 6. We have a negative pi over 6, right? But remember that we have our theta is it's equal to what? It's actually, sorry, the alpha is equal to 2 theta, right? So we would have pi over 6 and 2 theta equals to negative pi over 6. And we also need to probably add here plus a cycle, right? But let's see what we have. So theta in this case would be pi over 12, right? And it will also be, in this case, negative pi over 12. So that's going to be this. And then if we add, give me a second. All right. Ooh, wait, yeah. So, okay, so let me take that back a little bit. So we have the restriction on the theta, right? But here we have 2 theta. So now for 2 theta, the restrictions on the domain would be from negative pi to pi, right? Yes, so this is what we didn't included actually, because that will change, right? So if it was just without this 2, if it was just theta, then yes, we would include only positive pi over 6 and negative pi over 6. Since we have 2 theta here, we need to adjust our domain accordingly, right? So now we are looking at from negative pi, so all this semicircle or all the values up to the negative pi and up to the pi. So we go the counterclockwise direction until pi. So we essentially we have the whole circle, but just with the positive and negative uh, uh, version of that, right? So from here, then what we need is, so yeah, so we will keep plus and minus. So going back to my beautiful unit circle here, my square root of 3 over 2 positive is at pi over 6. And also, since we're also including the second quadrant, because pi is happening right here, we need to include all of the values that are square root of 3 over 2. So square root of 3 over 2 is here as well. So let me erase that. So my cosine is square root of 3 over 2 right here as well, right? So I will need to include that into my answer. So I have 2 more answers. So I have my 2 theta equals to 5 pi over 6. And then when we go, oops, when we go from 0 to the negative side or clockwise side, we said that square root of 3 over 2, so cosine is square root of 3 over 2 here, and also it's negative square root of 3 over 2 in here, because we're including from negative pi to 0 and from 0 to pi, so we need to include this answer as well. So that's going to be my so it's 7 pi over 6 if we go clockwise, right? But if we go counter sorry, counterclockwise. But if we go clockwise, that's gonna be the same as 5 pi over 6, right? So this would be negative pi over 6. That's gonna be negative pi over 2, pi over negative pi over 3, and that would be 2, negative 2 pi over 3, negative 3 pi over 4, and that would be negative 5 pi over 6, just going backwards, right? The to the negative first cycle, right? So we have 2 theta equals to negative pi, 5 pi over 6. And again, we'll have here theta equals to 5 pi over 12, and this one would be negative 5 pi over 12. So these are all your 4 answers for this specific example, okay? Again, restriction on the domain are important, right? So please be careful with those when you have some like 3 theta or 2 theta, that will affect your original domain, right? Because this is given for just theta. If you have 2 theta, you need to apply that to theta, right? So you will have just from negative pi to pi. Okay. Questions on that? All right. Then let me show you which one do I want to show you? Um all right. So okay, let me show you this one. That's kind of similar, I guess. So square root of 2 sine 3 theta plus 1 equals to 2. And the restriction is from 0 to pi. All right. Again, we just solve for sine 3 theta because essentially by the end we'll need to solve for this theta, right? So we'll have sine 3 theta equals to, so first I'll move this one to the other side, so I have minus 1, and then divide by square root of 2, so I have 1 over square root of 2, right? Which is sine 3 theta equals to square root of 2 over 2 if it's easier to see it that way, right? So now, restrictions on the domain. So we have for theta, it's from 0 to pi, and now if we multiply by 3, we'll have this is still 0, and this one will be 3 pi, right? So we have a circle or a cycle and a half of values that we need to include for our final answer, right? So that would be the full cycle until 2 pi, and then half a cycle until we have 3 pi. So we need to include all of those values into the answer for our theta, right? So now we have 3 theta equals to, when is my square root of 2 over 2? So I have a positive one, right? I don't have square anymore, so this one is just positive, and sine is positive in the first and in the second quadrant, right? So it's gonna be here and here. Here we have pi over 4, and here we have 3 pi over 4, right? And that's for just one cycle. And then for the second cycle, we need to add 2 pi and 2 pi right here, right? So I will have 3 theta is equal to pi over 4 plus, well, pi over 4, that's one answer, right? And then, so that's for this one. Then for the second answer, I have 3 theta equals to 3 pi over 4. That's the second answer. And then I also have, let me put it down. So 3 theta equals to, now after I make one cycle, I go back to the after 2 pi. So that would be my pi over 4 plus a cycle, right? So it's going to be pi over 4 plus 2 pi. And the last one would be 3 theta equals to 3 pi over 4 plus 2 pi, which makes it what? 9? pi over 4, and this one would be 11 pi over 4, right? So I have technically 4 answers, right? So my 3 theta is equal to pi over 4, 3 pi over 4, 9 pi over 4, and 11 pi over 4. But that's not the end, right? Because we need to get rid of this 3 now. So we need just to divide by 3 everything, or every single one of them. So my theta would be then pi over 12. Then it's going to be, so I'm dividing just by 3 here, by 3 here, 3 and 3, okay? So for this one, it's going to be just pi over 4. For this one, it's going to be now 9 divided by 3. So that's going to be my 3 pi over 4. And 11 pi over 3 times 4 is going to be 11 pi over 12. So these are all my 4 answers for this problem. Are we okay? All right, beautiful. And if you're not given any restrictions on your domain, like in this case, right, you can just write it in general. So you'll have 3 theta equals to, so when is your sign positive here? So it's at pi over 4 and 3 pi over 4. So you'll just write it pi over 4 plus 2 pi k, and you also have another one, which is pi over 4, 3 pi over 4 plus 2 pi k, where k is an integer. So this means belongs to, this means integer. All right. Yeah, so that's kind of it. So these are the problems for solving for theta, right? Now let me go over one more small topic that probably would be important. And we went over that today in class. I'll just want to reiterate a couple of more problems, I guess, so that you guys are more prepared. So let's say I have an example. So use, right, triangle to solve the following functions. So assume x is greater than 0, and we're working in the first quadrant just for simplicity. Okay, so we have cosecant of cotangent inverse of x. Okay, so if we're given something like this, we are okay. So as we said in class, let alpha be cotangent inverse of x, then cotangent, sorry, not cosine, cotangent. Cotangent alpha equals to x. Remember that cotangent alpha is, what is that? It's adjacent over the opposite, right? If we're looking at the triangle, right? So let's say this is my angle. So it's going to be this adjacent side over the opposite. Now, when we look at our cotangent, we have x, right? It's the same thing as x over 1. So my x is adjacent side, my 1 is the opposite side, right? So I can just write it here. X is this side, adjacent, and 1 would be the opposite. So for cosecant of alpha, right? So since this cotangent inverse of x, that's that we said that let it be an alpha. So cosecant is, what is that? It's hypotenuse over the opposite side, right? So for our beautiful triangle, we need to find what this hypotenuse is, right? For this one, we will use the Pythagorean theorem, right? So we have c squared equals to a squared plus b squared, where these are the legs. And this is my hypotenuse. So I need to find that hypotenuse essentially, right? So let me mark it as just, I don't know, A, for example. So, or C. just for, having the same value here. So C is equal to squared, right? Is equal to x squared plus 1 squared. Now C is equal to square root of x squared plus 1. And this is my hypotenuse essentially. So hypotenuse is x squared plus 1. And now I can write the answer for my cosecant alpha, right? So cosecant of cotangent inverse of x is the same thing as cosecant alpha, which is square root of x squared plus 1 over what? Over opposite side, which is 1, right? Over 1. Or you can just write it as square root of x squared plus 1, and that would be your final answer for this problem. Okay? All right, so let me go over another example. Let's say we have tangent. Well, this is very similar to that. Yeah, it's okay. Tangent of secant inverse of x over 2. All right. So let alpha be secant inverse of x over 2. Then what we need to find is tangent of alpha, right? That's the goal. And we know that tangent of alpha is opposite over adjacent, right? So that would be needed for us. Now, from here, if I want to convert it back to the normal form, I would have secant alpha equals to x over 2. And we know that secant is hypotenuse over the adjacent side, right? So again, if I draw a triangle and mark my alpha, or theta, if you want to use theta, doesn't really matter. So hypotenuse, in this case, that's the longest side. That's my x, right? And then the adjacent side, the one that is touching my alpha, that's going to be my 2. So I put it here. Now from here on, I will need to find this opposite side because that's what needed for my tangent, right? And I will again use the Pythagorean theorem. So I need to find this leg. Let me just write it as a opposite side, probably. That would be easier. So to find, okay, so x squared equals to opposite side squared plus 2 squared. This is just regular Pythagorean theorem. I need to solve for this opposite, right? Not for x. X is kind of, although it's unknown, it's still given to us, right? So I will be solving for this opposite side. So I have x squared minus 2 squared, and then I take the square root. I have opposite side equals to square root of x squared minus 4, right? And this is what my opposite side is equal to. So it's square root of x minus x squared minus 4. And yeah. And now I am ready to write my tangent alpha, which is opposite side over adjacent side, which is square root of x squared minus 4 divided by 2. And that would be the final answer for this type of problem. All right. So that's this. And then another one that I wanted to show you, this one is a little bit different. So please be careful with that. Let me see. Give me a second. Right. Okay. So that's gonna be okay. Found it. Okay, so cotangent inverse of tan alpha. Okay, now keep in mind right now, you need to notice that now it's not the same order, right? So before you had tangent of secant inverse. So first, this one is the outer shell is not inverse. The argument is inverse. This time, your outer shell or the outer function is inverse and the argument is just a function, right? So this is different. So in this case, you will solve it not the same approach as before. So you'll still need to use your right triangle, right? So now we will have, how do I start this? Okay, so tangent alpha, again, that's opposite over adjacent, correct? Right. So now if we say that this is my alpha, the opposite side would be here, and the adjacent side would be adjacent would be here, right? So tangent would be that. So we're not given any values for adjacent and opposite side. So you can technically write it as like A over B and just treat it as that, B, and that would be your C, the hypotenuse. Okay, you can do that. So now you need to remember this, what's it called? The identity, I guess. So tangent alpha is equal to cotangent of pi over 2 minus alpha, right? Where that comes from. Remember that the sum of all the angles in the in the triangle is 180 degrees, right? So 180. This one is already 90, right? So it means that this and this, so let me mark it as, let's say, theta, right? So that means that alpha plus theta should be equal to 90 degrees, or you also can write it as pi over 2, right? So if you solve for this theta, right, that would be pi over 2 minus alpha. And if you look at this angle, that would be your essentially pi over 2 minus alpha, right? So now when we work with the cotangent, whoops, inverse, right? We will substitute this tangent in the argument with the cotangent of pi over 2 minus alpha. So you'll have cotangent of pi over 2 minus alpha. Now remember that when we have cotangent inverse of cotangent or anything inverse of that same thing, that would be just this argument, right? So that would be equal to pi over 2 minus alpha. So that would be your answer for this problem, right? A little bit different, right? It's solved a bit different from what we had before. So I think that this way is a bit kind of more well, both are easy if you know what you're doing, right? But just keep in mind that the argument should be inverse and the function itself should be not inverse for this type of algorithm. For when you have the other way around, then you'll need to remember about this pi over 2 minus alpha thing, right? That the sums of the angles is 180 degrees or pi, and then this one is half of a pi. So the other two will end up being just pi over 2. Okay, so this is kind of the way that you solve it. And also, if you look at this from another perspective, so your cotangent of theta is, let me just write it. Cotangent of theta, what does it equal to? It's adjacent over opposite, right? But in this case, if we're looking at theta, your adjacent would be this side, which we call A, right? So it's A over opposite, which is this side, which we call B. So this marking was for the alpha, right? For the theta, that would be the opposite of that. So that would be A over B. And this is exactly my tangent alpha, right? So we can say that tangent alpha equals to 1 over, A over B, which is equal to cotangent of theta. And we said that theta, when we solve for it, is equal to, cotangent is equal to pi over 2 minus alpha. So this is how we can kind of prove that this identity, if we don't remember this identity, right? It's also kind of easy to see that when you work with the triangle. So I think that would be it. The rest I think we can go over tomorrow. Do you guys have any questions on the problems that we've covered so far? Okay.
No.
Then stop recording.